All right, so some quick review of some first semester stuff. Momentum, we already got from this one. D equals mv. Impulse. What is impulse? Besides a perfume that promotes someone suddenly buying you flowers. Yeah, I'm still waiting for someone to catch that reference, but anyway. Impulse, J or I, depends upon the mood of the author, is the change in momentum. That's all impulse is.
Isn't specific impulse the amount of change in momentum that a rocket is capable of? I think it has to do with how much fuel you have. Specific impulse?
I actually have not heard the term specific impulse. Generally, when you hear specific, it's per unit mass. So we would make it velocity.
Yeah.
I would not be surprised that there is something called specific impulse, but I'm just not familiar with it.
I may have what it just probably sometimes.
All right. Impulse also, if we think back to Newton's laws, F equals ma, which is m, change in velocity over change in time, which is change in mv over time, which is change in momentum over time. So change in momentum over change in time is equal to force. So change in momentum is also just force times change in time. So generally, in a physics class, if you're asked to find the impulse, you either use it with change in momentum or with force times time, average force times time, depending upon what you're given. If you're given force and time, you solve it this way. If you're given mass and velocities before and after, you solve it this way. And let's see, what else do we need before we shoot forward? Oh, formula for kinetic energy.
1/2 mv squared.
And I probably said it before, but if you would have me for the first semester course, then it would be something that everyone would respond in unison with. All right, so what I want to, pressure. What is pressure?
Force divided by area.
Yep. So what I want to do is I want to look at, I've got a box here with a bunch of particles moving all about, and some of them are banging up against the sides of the walls. Well, eventually all of them bang up against the side of the wall, but it's going to bang up against the side of the wall. So what I want to figure out is what is the pressure on this wall because of these particles. That's what we're going to start out with. This will connect into ultimately the atom, but we need to get there first. So, if I'm looking at the pressure within a certain amount of time t, well, particles are moving at some particular speed, and so if I'm restricting the time, not every particle is actually going to hit the wall. So I've got a certain number of particles in here which are could possibly hit the wall. So let's take a look at one of them that hits the wall and then bounces backwards. It comes in at, we'll just assume that is the positive direction. So it comes in with some mass times however fast it's going. So this is my initial momentum. My final momentum is negative mv, because it's going in the opposite direction. And so my change in momentum is negative mv minus mv, or negative 2 mv. So something that bounces back. So this is the amount of impulse that's exerted on the particle, so this is on the particle. Therefore, the particle exerts the opposite of that on the wall. Well, Newton's third law thing. So the impulse on wall from this one particle is just 2 mv. Questions up to here? Understanding up to here? Very good.
I think I understand, I was just writing stuff down.
Okay. Tom, you good?
Yeah.
Alright, good, alright. So if I'm looking at the force on the wall, or if I take this right here, I know that 2 MV is equal to the average force times whatever the amount of time was. Do I narrow it down? All right. Now, that's for one particle, except now I've got a whole bunch of particles that are actually hitting it. And so, make sure I'm doing this in the right order. And so that's per particle, that's for one particle. So if I'm looking at the total average force, total, that's just gonna be 2 mv times the number of particles that hit, divided by time.
And all.
That's COL for collision.
Oh. And.
Well, let's take a couple things into account now. Now, the number of particles that are actually going to collide with the wall is going to be some fraction of the total number of particles in the box. And so it's whatever the volume of this space is divided by the volume of the whole thing. I assume that the particles are evenly distributed throughout. So if this face right here, which is this face right here, has some area A, then this would be the volume of, I just call it DZ for danger zone, over the entire volume.
Is that n times?
Yes, that's times.
Okay.
And recognize that just because a particle is in this area doesn't mean it's actually going to hit this wall. On average, only half of them are going to hit the wall. The other half are moving in the other direction. So we throw an extra 1/2 in there. Now the volume of this DZ, or demilitarized zone, whatever you want DZ to stand for what you want it to stand. Well, this volume right here is just this distance, delta x, times the area. Depth times surface area. And delta x depends on how fast it's moving. So this delta x is just the speed in the x direction times delta t times the area. So we've now taken our equation there, and that the total average force is going to be equal to 2 mv over delta t times the number of particles that are actually going to collide, which is 1/2 times the total number of particles over the total volume times Vx delta t A. So basically, I'm taking this right here, substituting it in for VDZ, and then taking this whole thing and plugging it in for the number of collisions. Delta t is going to cancel. And so this and the 2 is going to cancel. So what I'm left with is the number of particles per volume times, I think I took care of that one, and now I'm left with, oh, and that's also a Vx because we're just dealing in this one direction here. So AMV Vx squared. We'll hold off on that for right now. So this is n divided by the v, now this Vx squared, I'm only looking at particle, or looking at what's happening in the x direction. Recognize it is a three-dimensional problem. I know that the actual speed squared is equal to Vx squared plus Vy squared plus Vz squared. If these particles in the box are truly moving in a random direction, then if I look at my average values, my average value of v squared, that should just be the average value of Vx squared plus the average value of Vy squared plus the average value of Vz squared. And these average values should all be the same. The average value of particles floating around in the box, there's no reason why they should be going in one direction any more than another direction. So this is just 3 delta V x squared. That 3 right there is going to become critically important later. So my average value of Vx squared is equal to 1/3 my average value of V squared. Just whatever, where V is just the speed of the particles, not in any particular direction. So this becomes NA over V times M 1/3 average value of speed squared. If I multiply both sides by V over A, because don't forget I have force right here, we now get, use that one already, use that, we're coming up to that. So if I multiply both sides by V over A, I get F times V over A is equal to 1/3 M V squared. That's pressure. So the pressure on the wall times the volume is equal to 1/3 of, well, that's just twice the kinetic energy. 2 times kinetic energy. Technically average kinetic energy. So this is 2/3. Questions up to here? All right. Ideal gas law. What is the ideal gas law? You had chemistry.
Long time ago. I don't think it's the ideal gas law. An increase in temperature means an increase in pressure?
That's built into the ideal gas law. That specifically though is, there's the 3 laws, I never keep them straight.
It's like
There's,
Boyle's law.
yeah, Boyle's law I think is volume and temperature.
No, Boyle's law is the one that doesn't have temperature, because it's Boyle and doesn't have temperature,
Oh,
I think. I might be wrong.
all right, so there's Boyle, Gay-Lussac, and what's the third one?
I don't remember.
One relates P and T, one relates V and T, and the other relates whichever the combination I didn't do, PV, PV, PT, VT. This is the
Yeah.
3. All right. Well, we can think through it. If the pressure, if I have a container that's set like this, if I turn the temperature up, what happens to the pressure?
It increases.
Increases.
Okay. If I want to keep the pressure the same, what would happen to the volume?
Increases.
It would have to increase, because the particle's moving faster, so you want to sort of, extend how long it takes for it to actually get to a wall or make the area larger. And if my temperature stayed the same and I want to increase my pressure, what would I do to my volume?
Decrease it.
Yeah. So in essence, pressure times volume is directly proportional to the temperature. Now, somewhere along the line, someone basically took Boyle, Ulisak, and Charles, he's the third one.
Yeah, I knew it started with a C, I was trying to think of it.
Took 3 laws and combined them all into one thing that just said that PV is equal to nRT. Or, pressure, volume, temperature. N is the number of moles. And if you've had chemistry, presumably that will bring back some really fond memories. And R is, it's a constant, I want to say Rydberg constant, but it's not, it's the ideal gas constant, something clever like that. Yeah, I didn't write down here.
It's PV times the number of moles, or Avogadro's number, times N.
Well, it's the number of particles divided by Avogadro's number.
Oh, okay, so that's N. Times something times the temperature.
So that's PV is equal to the number of particles divided by Avogadro's number, N sub A, that's, I think, the symbol for it, times RT. R divided by N sub T actually has another constant. It all depends upon which person came in. This is known as Boltzmann's constant, which I'll K sub B, Boltzmann's constant. And so we have PV is equal to capital N, K sub dt. And PV, we've already found that's 2/3 K, the kinetic energy. So my kinetic energy for particles in a box is 3 halves. Wait a second, I need to get rid of that N somehow. Where did I get rid of it? Oh, okay. So K over N. So total kinetic energy over the number of particles is 3 halves kBT. And this is just the average kinetic energy per particle. The key takeaway from this is that this is classical physics. In classical physics, the kinetic energy per particle is equal to 3 times 1/2 kBT. Where this 3 is the number of degrees of freedom. If I had particles in this box, they could go X, Y, or Z direction. There's 3 independent ways of going. If I had something with 2 degrees of freedom, then it would be 2 times 1/2, or just kBT.
But how are you physically gonna do that?
Shine a light. So, the whole point of this is to get to that one conclusion right there. That if I have a particle that is basically 2 degrees of freedom, in other words, I project it in one particular direction, so I've eliminated that degree of freedom because I know it's going that way, then, no, that's probably bad analogy with a particle in that one. If I shine a light, remember light is an electromagnetic wave. So if I shine a light in that direction, I've eliminated a degree of freedom, but my electric field is either basically will have a component this direction or a component in this direction. In other words, there are 2 degrees of freedom for the light. So therefore, my energy for light, put a little gamma there, the traditional symbol if you're talking about just electromagnetic radiation, is equal to 2 times 1/2, or kB times T. In classical physics, it was thought that the energy of light is directly proportional to the temperature. The greater the temperature, the more energy coming off of it. It works for particles, why not light?
That's not true, is it?
It is not. But we're getting to why this is of importance. All right, so now I need you to solve a problem. So putting that on the back burner for the moment, we're gonna do something else and then we'll connect the two. If I have 6 particles and 9 units of energy, how many different ways can I break up this energy? So for example, 9, 8, 7, 6, 5, 4. I could have 5 particles with no energy and 1 particle with 1 bit of energy. I'll do the next one. I could have 3 particles with no energy, 1 with 1 unit of energy, and 1 with 8 units of energy. So my total amount of energy is 9, and I'm breaking it up among, apparently 5 particles, make it 6 particles. 6 particles. And what I'm asking you is how many different ways can I do this? And we'd like you to take some time, work with each other, work solo, to tell me how many different ways I can divide 9 units of energy among 6 particles. For you math theorists, it's called the partition problem.
So 6. So that's a different number of combinations.
Yeah, with the different number of combinations that I'm basically adding 6 numbers together to get 9. That's, what are the different ways I can